Hello, and thank you for joining us for this presentation on Transcelestial. Today, I want to tell you about how we are unlocking last-mile connectivity with our CENTAURI wireless fiber optic products. Before we get into details, let me introduce Transcelestial. Transcelestial was founded in 2016 in Singapore with the aim of transforming the way the world gets connected to the internet. Our core investors are leading Singapore government funds such as EDBI, Seeds Capital, SGInnovate, and Vista. We're also backed by some of the top global deep tech investors such as Airbus Ventures. Early investment and support from Tekton Ventures, a subsidiary of Telecom with backing by the Ayala Corporation, shows the trust in our technology to help transform mega markets like the Philippines. So, let's set the stage for what we're doing today by telling you about what we call the Last Mile High-Speed Connectivity Challenge. This is a graphic of what we know as the core of the internet today. More than 99% of the world's data is shared across these continents through massive undersea cables. They carry an enormous amount of data. However, even when connected to the large continents like Africa or Australia, these cables only land in a few places. And while it looks like there's a lot of capacity here, in a few years, this way of connecting the planet will not be able to keep up with the exponential growth of demand for bandwidth. Why? It took 20 years to get to this point. Existing cables cost billions of dollars to deploy, they're difficult to lay, hard to repair, and they cost tens of millions of dollars to maintain every year. It has not gotten easier along the way. Each subsea cable still takes years to lay, starting with forming a consortium, raising funds, planning, and then laying the cable. Once the undersea cables make landfall, telecoms take that feed and plug it into Tier 1 and Tier 2 cities, then build connections out to towns, villages, and so on. Whether it's a huge landmass like the United States or an archipelago like Indonesia with 18,000 islands, only Tier 1 megacities get the most of the love. This is an economic decision because these are the locations where it's most profitable to connect people. And as a result, over half the global population lacks access to the internet. High bandwidth, low latency international transit data never reaches the masses. For developed countries, cities look like the picture on the left. Urban planning is usually fairly structured and methodical, where ownership of land and rights of way are clear. Deployment is relatively easy. In emerging countries, it's a bit more chaotic. From the outside, growth seems almost spontaneous, with people putting up buildings wherever they can find the space. How do you plan fiber deployments and reliably secure those, or manage your quality of service? And since COVID, internet usage has jumped by 25 to 40%. This sudden surge has actually taken many ISPs out of business and forced a few telcos to merge just to stay alive. Smarter ones managed to invest heavily in moving from copper to wireless connectivity and now to running fiber. To support COVID-inspired increases in streaming service usage during national lockdowns, the acceleration of a global shift to workplace as a service, and a surge in migration from on-premise to cloud-based infrastructure, ISPs and telcos now need to think of even faster ways to deploy high-bandwidth, low-latency internet access to residential as well as office buildings rather than to cell towers and central business districts only. And this problem will get worse with 5G adoption. True 5G, which some of you know as millimeter microwave, has a 500-meter range with a backbone requirement of a minimum of 10 gigabits per second. Today, only fiber can truly and consistently deliver those kinds of speeds. But to deploy that much fiber, that's a capex no one is looking forward to. So the question is there a way to capture the speed of fiber optics with the ease of deploying it wirelessly? Is there a wireless fiber optics? Well, of course our answer is yes. In the past, we might have called this free space optics or FSO. But sometimes when we talk about FSO with people who have been in the telecommunications industry for a while, we get this reaction. And we understand. FSO has earned something of a bad reputation for a few good reasons. It was cumbersome. Try fitting this thing on a telephone pole in Thailand or Vietnam. Setting up the equipment and getting proper alignment was also a massive challenge, and even then, reliability and conditions were rain, sunlight, scintillation, interference from other light sources, fog, haze and so on, well, it was dismal. And to top it off, it was expensive. You might wonder, what's changed? Yeah, we can understand the eye rolling, but this is not your father's FSO. Wireless fiber optics and laser communications are still a line-of-sight technology. However, there are strong benefits to having an optical connection between two systems without the need for fiber optic cable. By using the 1550 nanometer wavelength to transmit data, we can achieve very high throughput speeds with very low latency. And a major benefit of laser-based communication is that light is transparent to spectrum RF analyzers, and as such, these connections are also very secure. We've tried to combine the benefits of both fiber optic cable and wireless technologies, while also addressing several of the challenges presented by old-school FSO. So, enter CENTAURI. Again, our question was whether or not we could do something to address the drawbacks of FSO. And this is what set us on the course to building CENTAURI. With CENTAURI, we apply precision control on photonics and reduce the size of the equipment. On top of the benefits we mentioned a few seconds ago, we've improved upon legacy free space optics products. Today, CENTAURI can achieve much larger distances, much higher bandwidth capabilities than old FSO devices due to a complete redesign of the entire optoelectronics and optomechanics stack from the ground up. We have engineers who bring decades of learnings from NASA, ESA, and other defense agencies around the world who've been working on this technology at a strategic level into a commercial form factor and package. CENTAURI today is roughly the size of a rugby ball or a large shoebox. Third, CENTAURI requires less power to run than a standard light bulb in your house, around 20 or 30 watts only. And finally, our state-of-the-art pointing acquisition and real-time tracking system blows away any reliability concerns from previous generations of this technology with regard to rain, tower sway, other windy situations. So for us, this is a true Nokia phone to iPhone moment in this technology's history, with no offense to anyone from Nokia who might be in the audience. Here's another look at the differences between microwave, fiber optic cable, and wireless fiber optics. In many cases, our wireless fiber optics provides matching and even better performance. Fiber optic cable has higher latency and can be up to 30% slower than wireless fiber optics due to the light needing to travel through a fiber core and not air. Think about this while picturing hundreds of kilometers of fiber optic cable swirling around a city. Wireless fiber optics is, as we've said, very secure, and it's not interceptable or jammable. Microwave can be jammed. Fiber optic cable can be snooped. This picture shows a standard installation and setup of the CENTAURI point-to-point wireless fiber optic link. There are two options to power these devices, one via DC 48 volts, and the other via AC power over Ethernet that complies to 802.3 ATE/BT. This also allows users to power the device via PoE and DC to support power supply redundancy. The CENTAURI establishes a layer 1 data connectivity via SFP and SFP+ on either device. This data connection is completely separate from the management data link, which keeps data transmitted via the link secure. For alignment of the two devices, a router is used together with a mobile app to set things up. And the mobile app helps deployment and installers in the field set up and align the beam between the two devices quickly. Once started, the app guides users through the installation process, helping align the devices using a camera and a flashing beacon. With a couple more steps and confirmation from the app, installation is complete, the link is up, and data can begin to flow between the two devices. Over the last year, we've begun ramping up manufacturing of CENTAURI here in Singapore. This is really important because by setting up manufacturing in close proximity to our product and engineering team, we have a high degree of control over our quality, all of which is understandably important to our customers. Now I want to highlight a couple of use cases and share some information about actual deployments to give you an idea of what we've done to prove CENTAURI can deliver real-world results. Here's an example of what we call the urban connectivity use case. The top diagram shows the traditional way of laying fiber between buildings and base stations. The bottom diagram shows how deploying CENTAURI can be used to implement the same use case. These two ways of implementing connectivity are not mutually exclusive. Both of these networks can be connected to the same optical network infrastructure. As also shown in the lower diagram, CENTAURI can be used to implement multiple link hops to deliver connectivity over a longer distance. Here, the link between Building 2 and Building 3 shows CENTAURI as a relay, which extends the total distance of the link. And this is the big picture of different use cases. For backhaul, for LTE and 5G, enterprise leased line and home broadband, to backhaul for small cell on lamps or power poles, to connecting towns or villages to macro cells, or providing connectivity for rural or hard-to-reach areas where deploying fiber is too expensive or the right-of-way is difficult to obtain. And finally, to provide rapid deployment of connectivity for temporary sites such as conferences and events or disaster relief operations. And now on to some real-world deployments. In 2018, we conducted a pilot to see if we could improve the connectivity for a library in Seoul, South Korea. The library was within line of sight to an SK Telecom's building nearby. Working with the Telecom Infra project and Facebook, we helped deploy a prototype of our CENTAURI device, and everything worked like a charm. The only issue was that at the time, CENTAURI looked like a trash can, and it weighed about 5 times as much as it does today. It has definitely slimmed down a bit since then. Once we deployed CENTAURI in Seoul, the team flew back to Singapore and we began to monitor the link. Not long after, Typhoon Sulik arrived in Seoul, and according to our friends in South Korea, it was the worst typhoon to pass through there in over 10 years. It rains a lot in Singapore, but one day of rainfall during this typhoon equaled the average rain we get in Singapore over the course of an entire month. Let's just say it was really wet. And we were worried that the drop in visibility and the corresponding increase in precipitation would cause CENTAURI to drop its connection. What happened was that the CENTAURI's automated tracking system compensated for the impact of the rain by increasing power to the link, keeping the transmission rates well above the threshold where connectivity would have been lost. The two graphs here show the rainfall peaks and the correlating changes in throughput with CENTAURI. Certainly, the rain had an impact, but the link stayed up throughout the typhoon and recovered to maximum performance quite quickly. Here are some more photos of CENTAURI in its current form, being installed here in Singapore at the Port Authority Keppel location. And for reference, the model in the far right photo is 80 kilograms and 180 centimeters in height. This is another deployment we did in the Philippines. Apparently not to be outdone by South Korea and Typhoon Sulik, Typhoon Kamuri made landfall in the Philippines in December of 2019. With winds up to 220 kilometers per hour, CENTAURI braved the weather in part due to its being installed, properly, I might add, on a very stable pole. Again, the CENTAURI link remained up throughout the storm. Overall, we can say CENTAURI was less rattled by all of this than our team, who were actually stuck in the Philippines when the storm hit. So, is the last mile connectivity problem really solved? Today, we're on the way to seeing CENTAURI evolve and succeed in helping customers address their ground-based last mile connectivity challenges. And we're bringing better internet connectivity to hundreds of thousands of people. That's a game changer for sure. But what if you had the opportunity to transform the lives of billions of people, and for just a few $1 billion? At Transcelestial, we don't ask what if, we ask how, and we plan for when. Transcelestial's on a mission to move the global data backbone from underseas and between cities to space. With a laser mesh network consisting of over 700 microsatellites, we plan to augment and replace existing undersea and intercity connectivity, bringing high-speed internet within reach of everyone on the planet. Ultimately, the cost per bit and the data rates we plan to roll out will be an order of magnitude better than current satellite-based communication solutions and will match or exceed current intercity fiber speeds in many countries. We're already laying the groundwork for the launch of a mini constellation of microsatellites that will circle the equator in low Earth orbit as a first step towards this overarching goal. We'll announce more on this in the next few months. Thanks very much for your time and interest in our presentation. If you want to learn more about Transcelestial and our products, please visit our website or chat with us today.